Warp drives may or may not be possible, but if they are, then what if a distant alien civilization's warp fields could produce gravitational waves visible here on Earth? Well, according to a recent study, that may be the case. We are entering a golden era of gravitational wave astronomy. Over the past 9 years, LIGO, the Laser Interferometer Gravitational Wave Observatory, has found around 90 mergers between black holes or neutron stars, with sensitivity increasing with each new observing run. Using everything we've learned from LIGO, we're now planning the next generation of detectors like Cosmic Explorer, the Einstein Telescope, and the newly approved Laser Interferometer Space Antenna, LISA. We have a good idea of some of what these detectors will see, from spinning white dwarfs to merging supermassive black holes. But what will they find that we aren't expecting? Whenever we open a new window to the universe, we find unexpected phenomena. Maybe in one of these windows, there be aliens. Specifically, if there are advanced alien civilizations out there, and if these civilizations travel the universe with warp technology, could we detect signatures of the massive distortions in space-time caused by those warp bubbles? Well, we wouldn't be doing this episode if the answer wasn't at least a remote maybe. Specifically, a new study finds that the collapse of a warp bubble of moderate size within our galactic neighborhood should be visible as gravitational waves for future detectors. Let's pick this apart to see if and when we'll discover our first alien warp bubble. But first, to recap. Warp drives have long been a useful tool in science fiction to evade the pesky speed limit of the universe, light speed. But then, back in 1994, Mexican physicists Miguel Alcubierre found a solution for the superluminal warp field within the classical framework of general relativity. Obviously, we covered this in a previous video. The loophole that Alcubierre used is that while it's impossible to travel through space faster than light, there's no limit to the speed with which a patch of space can move relative to another patch. We know for sure that this superluminal relative motion of patches of space occurs. For example, two sufficiently distant regions of the universe are moving away from each other faster than light due to the expansion of the universe. And we can think of the space beneath the event horizon of the black hole as moving at superluminal speeds relative to the distant exterior. The Alcubierre warp field works by expanding space behind a patch of space and contracting it in front, which ends up pushing this bubble of space forward. And because general relativity allows it, there's no fundamental limit to the speed that bubble can reach. So now just put a spaceship in the bubble and you have a warp ship. So why don't we have our own warp drives yet? Well, because they may be impossible, and even if they're possible, they have some pretty insane requirements. The Alcubierre warp field is a valid solution to the Einstein equations. Those equations relate the geometry of space with the mass and energy that space contains. The geometry is captured by the metric on the left side of the Einstein equation. Almost any imaginable space-time geometry can be described by the metric, including the Alcubierre warp field. The equations of general relativity then tell you what distribution of mass and energy space needs to contain in order to be warped by your chosen metric. That's the stress-energy tensor on the right. But not every imaginable metric corresponds to a physically possible mass-energy distribution. The Alcubierre metric looks to be one such impossible configuration. For one thing, it violates something called the null energy condition. Put simply, to curve space as the warp metric demands, the corresponding stress-energy tensor demands a space containing an enormous amount of negative mass. Unfortunately, this so-called exotic matter is almost certainly not possible. Workarounds have been discussed, like using the Casimir effect. Eric Lentz even came up with a warp solution that may not require negative mass, although even this suffers from the other big problem of the Alcubierre field. The amount of energy required to move even a small vessel capable of carrying people is estimated to be the mass energy equivalent of anything between a large moon and an entire star. We have a video on some of those recent alternative proposals, but the new paper by Katie Clough, Tim Dietrich, and Sebastian Kahn goes back to the OG Alcubierre field. They make no claims about the physical or practical possibility of constructing this field in the first place. Instead, they ask what really happens to a warp bubble after the fact, assuming it somehow gets made. And of utmost importance, they ask, does a warp bubble produce gravitational waves that we could detect? So the Alcubierre metric describes a bubble of space that can travel faster than light. When in motion, though, at a constant velocity, the warp bubble should not produce any gravitational waves. It should produce them when accelerating or slowing down, or perhaps when forming or switching off. In short, when the warp field is undergoing some evolution over time beyond constant motion. Unfortunately, the Alcubierre solution doesn't say anything about how the metric should evolve over time. And this is what the researchers explore in detail in their paper, the natural evolution of an Alcubierre bubble according to general relativity. This is no easy calculation. Understanding the time evolution of a metric and its corresponding mass-energy distribution requires something called an equation of state. In the paper, the authors point out that there's no known equation of state that would sustain the required metric over time. That means it's not enough just to have this exotic matter, you also need a yet unknown behavior of that matter to lead to the also yet unknown equation of state to sustain the bubble. But let's assume some advanced civilization figures out how to make exotic matter and contain it so that it holds together for the journey across the galaxy. Again, at constant velocity, space-time would be perfectly flat far away, meaning you wouldn't have any observable gravitational waves. But we also know that the warp bubble does not hold its shape if the delicately engineered drive stops constraining exotic matter with the required equation of state. So what happens when the drive is switched off, or what happens when it fails? In the latter case, it's probably very bad for the aliens, but maybe good for us because it would produce observable gravitational waves. So how do we calculate what happens when you burst a warp bubble? Well, it's not easy. While Einstein's equations are very elegant, the calculations can become horrendously messy. After all, we're trying to evolve complex distributions of matter through 4D spacetime. For this reason, the researchers used numerical relativity simulations, which means calculating each time step based on the previous time step. To do this, they needed to split 4D spacetime into slices of 3D space, or hypersurfaces, at consecutive times. The aim is a sort of flipbook in which each page is a 3D spatial volume, and flicking through the pages gets us the evolution of that space and so reconstructs a 4D spacetime containing the evolving metric. So they rewrite the Alcubierre metric in terms of a three-dimensional metric that lives on the hypersurface and introduces a few functions that tell us how to translate between different ways of slicing different hypersurfaces and how they embed into the overarching 4D spacetime. The starting metric on the first page of the flipbook has a corresponding initial configuration of matter, and that matter should evolve as the metric evolves. So far so good. Up until now, this has all been pretty standard practice for simulating general relativity. This is the same framework we'd use to tackle more realistic, dare I say, mundane problems like the merger of two black holes. But simulating warp drives is not such smooth sailing. Remember that we need this equation of state thing in order to evolve the Alcubierre metric and the corresponding mass-energy distribution over time. And remember also that we don't know of an equation of state that allows the metric to be stable. But that's okay, because we're trying to see what happens when the warp bubble fails. This means it's possible to come up with a workable equation of state for a failing warp bubble with admittedly a few speculative assumptions about things like pressure, timescale of decay, and the resulting matter after the collapse. Even if these assumptions about the equation of state of non-existent matter are about as accurate as assuming a spherical Klingon in a frictionless vacuum, the point is that even with sensibly imperfect assumptions, we can still learn something about the physics, as well as progress with the calculation, which is always nice. So, we've set up the first page of our flipbook, one of our hypersurfaces with a matter configuration which in turn gives us our desired Alcubierre metric. We've specified the equation of state, and so we are ready to simulate. By specifying these initial data, Einstein's equations and the equation of state take over, and the computer can evolve the geometry of the spacetime and the distribution of our matter from one hypersurface to the next. Once we reach the final hypersurface flip page, we can stitch together the spacetime again and watch as it evolves through the 4D simulation. So, how exactly does it evolve? Let's say an advanced alien species takes a trip to see their cosmic neighbors. On this occasion, they allow a new recruit to pilot the warp drive. Everything's going great until they miss a warning light coming from the matter containment field, and the warp bubble bursts, destroying the ship and the crew in the process. We've all been there. Or, depending on exactly how this stuff works, maybe this was a controlled dispersion of the warp bubble once they reached the destination, but the catastrophic version is likely to make bigger waves and also better represents the simulation in this paper. The first thing that happens is that the warp bubble collapses inwards, presumably obliterating the ship, and then expands outwards at the speed of light. That outward expansion is accompanied by a series of gravitational waves, ripples that follow the massive fluctuations in space-time curvature of the ruptured bubble. So, what would these waves look like to us? Well, the signal shape would be very different to the black hole or neutron star mergers that we've seen. In fact, the researchers liken the signal to the head-on collision between black holes, but without the characteristic ring down at the tail end as the merged black holes settle down. That means if we could detect such an event, it would stand out as not being from a natural source. But could we detect these gravitational waves in the first place? Well, the study calculates that the collapse of a 1 kilometer radius warp bubble traveling at 10% light speed would produce a signal at the Earth with a strain of 10 to the power of minus 21 if it happened 1 megaparsec away, or a bit further away than the Andromeda Galaxy. Now, a strain of 10 to the power of minus 21 means lengths here would be shifted back and forth by a factor of 1 over a billion trillion. That sounds tiny, but that's exactly the strain limit that LIGO can detect. So can LIGO detect bursting warp bubbles in Andromeda? Not quite. The frequency of this 10% light speed kilometer radius warp bubbles gravitational waves are 300 kilohertz, which is way higher than LIGO's sensitivity range. Now, while high-frequency detectors operating in the mega or gigahertz range are being considered, focus for now is on much lower frequency sources, the larger, slower natural phenomena that are much more likely to be real. So, for the time being, don't expect headlines saying we've detected gravitational wave signatures from a stalled, hyper-advanced extraterrestrial warp drive. But it is pretty exciting that the detector capable of seeing such a thing is within our technological grasp. And although any signal is well outside LIGO's frequency, it's possible that the gravitational waves from a burst warp bubble will appear even stronger than that 10 to the minus 21 strain. For example, if it's from within our own galaxy, then it's much closer than 1 megaparsec, and so will be louder. If the warp bubble is traveling faster than 0.1 C, then it emits more intense gravitational waves on bursting. But 10% light speed requires a mass energy equivalent of 1% the speed of the sun, so let's not get greedy. I should also add that while superluminal speeds are technically possible with warp bubbles, in the words of the authors, these would likely lead to pathologies, aka physics breaking, and anyway requires computational resources beyond that study to investigate. There's some other good news. If we do detect the gravitational wave signal of a bursting warp bubble, we may see more than just those waves. After the bubble collapses, the exotic matter escapes, waves of positive and negative energy, which might lead to an electromagnetic counterpart to the gravitational wave signal. We call such signals multi-messenger events, and we routinely search for these other messengers, typically photons and neutrinos, for every gravitational wave that we see. We routinely do see the electromagnetic counterparts of neutron star mergers, for example. Look, even if we never detect an alien warp signal, perhaps because they don't exist, this type of research is still interesting. Warp drives may have their issues, but they are motivated by the extremely well-tested theory of general relativity. It's instructive to poke at the edges of such theories to test the limits of their validity and to come to a better understanding of what's actually possible and what's not. We can add new intuition and techniques to our toolbox for understanding the possible universe. Or, far less likely, but who knows, we build the high-frequency gravitational wave detector and immediately witness the gravitational pop, 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 the unmistakable bursting of bubbles of warped space-time. Whenever we open a new window on the universe, we discover things that no one expected. Our newfound ability to measure the ripples in the fabric of space-time, gravitational waves, is a very new window, and so far we've seen a lot of wild stuff. We've observed black holes merging, and their oddly high masses challenges our understanding of black hole formation and growth. We've seen colliding neutron stars that have forced us to rewrite our ideas of how many of the elements of the periodic table get made. But what else might be hiding in the ripples of space-time? Oh, I know. How about the gravitational wakes caused by planet-sized alien spacecraft accelerating to near light speed? The Laser Interferometer Gravitational Wave Observatory, LIGO, was built with some very particular natural phenomena in mind. In particular, merging black holes and neutron stars, which we've now seen, and supernova explosions, which we haven't yet. Gravitational waves are produced whenever an object with mass is accelerated, and so we're constantly bathed in a complex network of space-time ripples. LIGO could only see the most powerful of these, caused by very massive objects undergoing extreme acceleration, and those only within a certain frequency range. Still, it's worth asking, what else might LIGO be able to see? For example, could an alien spacecraft be massive enough and accelerate rapidly enough to produce observable gravitational waves? Well, that was the question asked by Luke Sellers and team. Their recent paper introduces the Rama craft, the Rapid and Massive Accelerating Spacecraft, a ship that creates a wake of detectable space-time ripples. But just how massive and how rapidly accelerating and how close to us would a Rama craft have to be for LIGO to be sensitive to it? Well, let's find out. Let me add a couple of notes of caution. First, this paper has not yet passed through the peer review process, although you can get it on the preprint archive. Second, we have not observed signals like this, at least as far as anyone has noticed. The paper is extremely speculative, and in a way it's just a bit of fun. But beneath the fun premise, the paper asks a serious question. Given LIGO's capabilities and known sensitivity, what kind of other signals might it be capable of detecting? First though, a brief reminder about gravitational waves and LIGO. We've covered this stuff before, of course. Now, Einstein's general theory of relativity predicts that accelerating masses create self-propagating ripples in space-time, just as accelerating electric charges make ripples in the electromagnetic field, also known as light. Gravitational waves are waves in the fabric of space and time. They change lengths and durations as they pass by. LIGO spots gravitational waves by detecting the tiny variations in the relative lengths of its 4-kilometer-long arms. Those arms alternately grow and shrink as the wave passes by, and from the pattern of those changes we can identify the nature of the gravitational wave source. The two LIGO detectors in Washington and Louisiana in the US, and with the help of their cousins, the European Virgo and the Japanese Kagra, can triangulate the location of the source of a gravitational wave. Now, it's super easy to make gravitational waves. Just flap your arms up and down, and you're emitting gravitational waves. But making detectable gravitational waves is a different story. Gravity is by far the weakest force, so while our electromagnetic signature of our little chicken dance is all too observable, you're effectively invisible in gravitational waves. To make detectable gravitational waves, you need really big masses and you need to wiggle them really, really hard. For example, a pair of black holes in a binary orbit are accelerating towards each other and so generate gravitational waves. These waves carry away energy, causing the black holes to sink closer together. In a tighter orbit, they move faster, and the stronger acceleration results in stronger gravitational waves at higher frequencies. If a pair of black holes the mass of our Sun were to spiral together, then just before merger, they'd be moving at roughly half the speed of light. And the power they radiate in gravitational waves is more than the power emitted in light by all the stars in the observable universe. And this is what LIGO was designed to be sensitive to, the most powerful bursts of waves emitted right at the end of such an in-spiral. I made a point of emphasizing that it's not the speed of the black holes that creates gravitational waves, but rather the acceleration. More precisely, it's the change in the quadrupole moment of the mass distribution, but let's just think about acceleration because that's what we need for today. A black hole moving at an insane but constant speed in a straight line wouldn't emit waves, but orbiting black holes do emit waves because they're accelerating towards the center of mass of the binary system. But there are potentially other types of acceleration besides orbits. For example, we have linear acceleration, just good old speeding up in a straight line. So what speeds up in a straight line? Well, people trying to get somewhere. So what if those people are aliens yeeting themselves through the cosmos? In the paper we're looking at today, the team does a pretty straightforward general relativity calculation to figure out what the gravitational radiation should look like for a massive body accelerating at a constant rate. And importantly, in what circumstances LIGO could detect that. Gravitational waves in four-dimensional spacetime are hard to visualize, so let's start with an analogy. Waves on the surface of water. An in-spiraling orbit is a bit like stirring the water in circles. The ripples expand outwards. But a linearly accelerating object makes something more like the wake of a boat. And it's this wake that would wash over the Earth and LIGO, and we could potentially detect. In order to figure out what types of spaceship wake LIGO could detect, we need to work backwards. We need to figure out the mass and acceleration rate that would produce a gravitational wave with the right intensity and frequency to be detected by LIGO. Let's start with frequency. Just like with telescopes, LIGO is optimized for a specific range of frequencies. It's sensitive to gravitational waves between a few tens of hertz to a few thousand hertz, with the sweet spot somewhere in the middle of that range. Outside that range, the noise gets too loud and tends to drown out real signals. The frequency of a gravitational wave is roughly equal to the frequency of the phenomenon that produced it, or the inverse of the timescale of that phenomenon, which would be the orbital period in the case of in-spiraling objects. LIGO is designed to be most sensitive to the frequency of in-spiraling black holes just before they merge, and particularly to the mass range expected for black holes produced in the death of massive stars. It's just a coincidence that the resulting frequencies are in the range of human hearing, as long as you convert the gravitational wave to a sound wave first. Okay, so what frequency is a spaceship wake? It's a little more complicated than the frequency of a black hole merger. The gravitational wave signal ends up being a mix of frequencies, some high, some low, but crudely speaking, larger acceleration means more energy emitted in higher frequency waves, while lower accelerations have stronger low frequency waves. For an accelerating spacecraft, it's nicer to think about this in terms of the time spent accelerating. If we assume that the aliens want to reach a certain maximum speed, say a certain fraction of the speed of light, then the acceleration is determined by the amount of time taken to reach that speed. The longer the acceleration time to reach a given speed, the stronger the low-frequency waves will be. We can also think about this in terms of wavelength. Low frequency means long wavelength, and the longer our craft spends accelerating, the longer the gravitational wave it can emit. Based on LIGO's frequency sensitivity and assuming acceleration to 30% the speed of light, this team of scientists figures that they'd need to reach that speed from standstill in just a few tenths of a second in order to be detectable by LIGO. And that's really slamming the foot, or the pseudopod, or the plasma tentacle, or whatever, on the gas pretty hard. But just how massive and how nearby would such a craft need to be in order to be detectable by LIGO? Well, the more massive the craft, the stronger its gravitational wake. Now, LIGO is a very sensitive instrument, capable of detecting changes in the lengths of its arms by 1,000th the width of a proton, and that lets us spot black holes merging 1 billion light years away. In fact, LIGO could also detect acceleration of a starship an entire universe away if that starship had the mass of the entire Sun. That's a solar mass accelerated to 30% light speed in a fraction of a second. Not too plausible, perhaps, although we are talking about the hundreds of billions of galaxies, each with hundreds of billions of stars, and we just need one civilization in all of that to reach this frankly absurd technological power. Still, it sounds pretty iffy. But thinking more modestly, how massive would the craft have to be in order for an acceleration inside the Milky Way to be visible? Well, from the other side of the galaxy, it would have to be the mass of Jupiter. Moving a Jupiter mass to a good fraction of light speed in less than a second is still pretty far out, and still doesn't seem likely that such insane levels of tech exist in our galaxy, given that we don't see any other evidence for it. If this were to happen closer to Earth, say within 30 light years, our local stellar neighborhood, then we could potentially detect a moon mass accelerating ship. Some of you may remember that warp fields do require the entire mass energy of a star or of Jupiter or of a moon, depending on how you calculate it. Now, maybe that's a way to produce the stupid accelerations required, while at the same time protecting the Rama craft from the cataclysmic g-forces of that acceleration. Unfortunately, the known warp-filled solutions don't produce the same space-time wakes as simply accelerating a large mass. But perhaps there are undiscovered warp solutions that can do this job. But however they do it, the aliens are going to need to access an unthinkable amount of energy. Remember that a single merging black hole binary produces more power in gravitational waves than are emitted by all the stars in the universe, just for an instant. Scale that down to a mere planet mass craft, and we're still talking entire galaxies, or at least many stars worth of power. This all sounds pretty out there. But this isn't quite a fool's errand. There are a couple of good reasons that we might want to think about weird sources of gravitational waves, whether Rama craft or otherwise. We mostly think about looking for aliens through electromagnetic radiation, whether they're radio transmissions, they're planet-covering city lights, or the light blotted out by their Dyson spheres. But the problem with electromagnetic waves is that they dim very quickly with distance. The intensity of light drops as the square of its distance. Double your distance from a light source and it's quarter the strength. 10 times further away and it's a factor of 100 fainter. In addition, electromagnetic observatories, especially traditional telescopes, but also to some extent radio observatories, tend to be limited to relatively small patches of the sky at a time, which further slows the process of looking for this stuff. Due to this, our searches for artificial electromagnetic signals are pretty much limited to nearby stars in the Milky Way. For example, even the most ambitious search to date, Breakthrough Listen, has an ongoing goal of observing 1 million stars and a handful of exotic candidates, requiring literally years' worth of observing telescope time on some of the biggest radio dishes in the world, and that's just a fraction of a percent of the stars in the Milky Way. In contrast, the strain or stretching and squishing of space caused by gravitational waves weakens not as an inverse square law, but just as an inverse law. Being 10 times further away only means being 10 times weaker in strain versus being 100 times weaker. Another convenient fact about gravitational waves is that they pass through anything. Photons are easily blocked by a bit of dust between the stars or by our atmosphere, but gravitational waves are literal space-time ripples. All the matter they pass through just kind of wiggle wobbles a bit, and the wave passes by largely unaffected. So we are able to monitor gravitational waves coming from all directions constantly and to very large distances. So if that gigatech civilization is out there with its stupidly large spaceship, we will detect it, as long as it's close enough. Now, there are other gravitational wave observatories that can or will do better than LIGO in some respects. The upcoming LISA, the Laser Interferometer Space Antenna, will have arms 1,000,000 times longer than LIGO, and that means it's sensitive to frequencies almost 1,000,000 times lower. It's a little complicated to make a direct comparison of frequency sensitivity, but adding the fact that LISA is able to monitor uninterrupted for many days due to the lack of gravitational noise out there in space means it should be able to detect Raman craft that take several days to accelerate. Then there's the Pulsar Timing Array, a gravitational observatory consisting of pulsars scattered across the Milky Way. It could be sensitive to craft that accelerate over months or years. Now, these craft still need to be of Jupiter-ish masses for us to spot them from across the Milky Way, but now at least the aliens don't have to get whiplash from the G-forces in order to be seen. We probably are not going to see Raman craft. They're just a bit too outlandish to be likely. On the other hand, we would not want to miss them if they exist. And on the other hand, we may well see signals with LIGO and its relatives and successors that look like linearly accelerating masses. And this paper does a good job of laying out what the physical conditions of such phenomena would have to be for us to spot them. For example, we could have orbiting black holes with highly elongated orbits, or maybe a star or giant planet accelerating as it plummets into an enormous black hole, or some weird type of supernova where an intact chunk of its core gets exploded out. The universe does weird stuff all the time, and it's good to know what to look for, as long as we don't immediately conclude that it's aliens, because it's never aliens. But it would be cool to find out that there are planet-sized spacecraft hooning around the other side of the galaxy, leaving us sloshing around in their wakes of rippling space-time. We are the middle children of history, born too late to explore the Earth, born too early to explore the universe. To partially quote someone on the internet whose wisdom is only matched by their anonymity. In the far future, we may have advanced propulsion technologies like matter-antimatter engines and compact fusion drives that allow humans to travel to other stars on timescales shorter than their own lives. But what if those technologies never materialized? Are we imprisoned by the vastness of space, doomed to remain in the solar system of our origin? Perhaps not. A possible path to a contemporary cosmic dream may be to just build a ship that can support human life for several generations, a so-called generation ship. Faster-than-light travel is almost certainly impossible. So says Einstein's special theory of relativity, and we rarely win when we bet against Einstein. That sounds like bad news for the galactic future of humanity, given that the Milky Way is 100,000 light-years across, and there are relatively few stars in what most would consider to be a reasonable commute. But that doesn't mean we can't reach for the stars. If we could build spacecraft capable of reaching 80, 90, even 99% the speed of light, then relativistic time dilation would slow the clock of the spacecraft relative to Earth's. At these speeds, a single crew could reach an interstellar destination up to hundreds of light years away within their own lifetimes. But such speeds would require some pretty out-there propulsion methods like matter-antimatter engines, compact fusion reactors, or even black hole drives. And even if we eventually do build such devices, there are a whole range of dangers that uniquely arise when travelling through the cosmos at such high speeds, as we've discussed previously. So, what if it turns out that we have to travel the slow road? What if it proves impossible to send humans any faster than a tiny fraction of the speed of light? Or what if we decide that we really need to leave Earth ASAP using technology that we at least understand today? Okay, here's the scenario. Something is coming. It could be a comet impact or catastrophic climate collapse or the Trisolaran fleet. Whatever it is, there's enough of an existential threat that we decide to ensure the future of our species by trying to settle another world. Quite naturally, NASA tasks PBS Space Time with planning a mission to settle Proxima Centauri b in the Alpha Centauri system. This is the closest known exoplanet to Earth, a mere 4.2 light years away. To keep things simple, let's pretend that we discovered that Proxima b is already habitable, so all we need to do is get some people there in good condition. We only have a few decades to make this happen, so ultra-advanced propulsion is out of the question. We launch whatever we can throw together in around 30 years. The fastest ship we could conceivably hope to build might reach speeds of 10% that of light. That's a 42-year journey. Launch a crew in their 20s and they'll arrive at retirement age. More likely, our craft will travel much slower, so no crew that starts the journey will live to see its end. Assuming that cryogenics won't be 100% reliable within decades, which is a pretty fair assumption, it sounds like we need to plan for a mission in which multiple generations of humans are born, live and die en route, and that landfall is made by the descendants of the launch crew. It sounds like we need to plan for a generation ship. There are lots of decisions to make in how we do this, but remember our constraint. It has to be something we can plausibly launch in 30 years. We're going to need to choose a propulsion system, a crew size and composition, life support systems, and finally, we need to ensure the mental, social and cultural well-being and stability of this group. Starting with the propulsion method, this determines the speed we can travel, the potential size of the ship, and so the size and number of generations of the population we need to sustain. The fastest vehicle ever built by humans is the Parker Solar Probe, which accelerates by blasting a propellant, hydrazine in this case, using electrical power, although it was really more the gravitational assists that enabled the Parker to reach 700,000 kilometers per hour. If we could scale up this tech to something large enough to carry lots of humans, then at this speed we could get the crew to Proxima b in 6,300 years. It's like 200 generations, and roughly the length of recorded human history. It's difficult to imagine that nothing would go wrong in that much time, but we're also pretty sure that we can get a ship to this speed, so we should see if this timescale is at least feasible. Also, this is the speed assumption made by French scientists Frédéric Marin and Camille Belloufi in a series of studies, and we'll be coming back to their conclusions regarding a trip of this length. We'll also consider a much faster craft, one propelled by nuclear fusion, smashing light elements together to form heavier elements plus lots of energy, just like our sun does. We haven't yet managed to build a commercially viable fusion reactor, let alone the sort of compact reactor we need for a spacecraft. But there is a fusion technology that we've thoroughly mastered, and that's the thermonuclear explosion. There are various concepts for spacecraft that accelerate under a series of fusion pulses, aka explosions, rather than sustained fusion reactions. These vary in sophistication from the more advanced internal confinement engines of Project Daedalus to more achievable, if scarier, proposals where you literally detonate thermonuclear explosions behind the craft, like Project Orion or the Ensman starship, or into a forward sail like the Medusa design. Top speeds for some of these have been estimated at 30% light speed, but that's highly optimistic. A little under 10% is more realistic for a mature version of this technology. For us, with our limited timeline, we're going to assume we can get to 3% light speed. That's around 50 times faster than our conventional drive, so it gets us to Proxima b in a mere 140 years, just 4 or 5 generations. So, today, we're going to plan towards these two travel times, 140 years if fusion pans out, and 6,300 years if not. we'll have teams working on both, and you can think of these as representing the extreme boundaries of what we can achieve in the little time that we have. The next decision will influence all of the choices that follow. How many people are we sending? This determines the size of the ship or ships and the resources we need to bring. Perhaps the most important factor determining the population size on a generation ship is the issue of genetic diversity. There are two aspects to this. How many people are needed to ensure a healthy multi-generational crew during the journey, and how many are needed to healthily populate a new planet? A 6,300-year journey means 200 generations, give or take. If the genetic diversity of the starting population isn't sufficient, there'll be genetic health issues en route. Moran and Belufi explore this question in a 2018 paper. They use Monte Carlo simulations to calculate the minimum number of humans that would be needed to avoid many of the potential genetic pitfalls, also accounting for various forms of misfortune, such as random disaster eliminating a third of the population, different infertility rates, and even an overall chaotic factor intrinsic to any human exploration. From all of this, they came up with the minimum numbers needed to achieve sustainable population during the journey. They conclude that we need to launch with a crew of at least 100, who will multiply to a population of 500, and that's the level we need to support for most of the journey. How big a ship does it take to comfortably carry 500? Well, SpaceX's Starship is supposed to be able to carry 100, so the equivalent of 5 of those, at least. However, that doesn't include the space needed for systems to support 500 lives long term. For that, we're definitely going to need a bigger boat. Missions around the solar system don't need to be luxurious, but centuries or millennia long trips to Proxima b will need some home comforts, like gravity. Living in zero gravity or microgravity has clear negative effects on health, with the most well documented being on bone density. To avoid our travellers reaching Proxima b as Wall-E-esque gelatinous blobs, we need artificial gravity. We've discussed previously how this could be done. There really is only one way, and fortunately it's not that complicated. The ship's habitats need to be spun in a circle to give 1g of centrifugal acceleration, perfectly mimicking Earth's surface gravity. There are lots of designs for centrifugal artificial gravity, but the simplest might be a rotating ring habitat. A 100-meter radius ring would need to rotate 3 times per minute to replicate Earth gravity. That seems not completely crazy, so let's just move on. The next step is to feed our crew. Another study, led by the French team, finds that we'd need 0.45 square kilometers for an omnivorous and balanced diet. Now, our 5 starships have a surface area of about 1% of that. So we'd either need to send 500 starships just to feed our crew, or find a way to produce food more efficiently. That 0.45 square kilometers is dominated by the space for raising livestock, so burger night might be the first thing we have to cut. It's possible to get the required area down to 0.015 square kilometers if we grow nutrition-dense crops like sweet potatoes using our best hydroponic or aeroponic systems. That's just 30 starships worth of farm, so we're back to the realm of the sane. The crew is also going to need some protein. Now, maybe we can get the quantity and variety from an efficient veggie protein source, especially with a little genetic tinkering. But if not, there are plausible meat options. Now, lab-grown meat technology is a bit speculative at the moment, but there is a very well-established carnivorous option suited to the less squeamish interstellar traveller. I'm talking about insects. For example, mealworms can be farmed at high densities and provide extreme protein richness. 1 to a few starships worth of mealworm farm might do the trick. Overall, we're going to need something like 6 to 10 times our crew's living space for food production. And that's for a pretty boring and slightly crawly diet, but maybe there are some gourmet yam and grub recipes just waiting to be discovered. A bigger challenge than food is the water, which our travellers need in order to grow that food and also in order to just live. An adult human needs around 2 litres of water per day, give or take. 500 humans need 1,000 litres per day. That's a cubic metre weighing a metric tonne. Our 140-year journey may be able to haul the required 50,000 tonnes of water, just barely, but forget about it for our 6,300-year slog. In either case, we're going to want a very good water recycling system. Just recently, the ISS reached a new milestone of 98% water recycling efficiency. Now, if that's as good as we ever get, then for our fast mission, we need a more reasonable 50-tonne supply of reserve water, perhaps one starship worth of water storage in terms of volume. But for our 6th millennia mission, we need 50 times that. So our generation ship just doubled in size just to haul enough water. And remember that we haven't even considered the water used and lost for growing food. Maybe add as much water again for 100 starships in water. In order for the long trip to be plausible, we may need to focus on improving our water recycling. Get it to at least 99.5% efficiency, which brings the reserve storage requirement down a factor of 4 to a similar scale as our farm requirement. There is perhaps one upside to needing to store all this water, and that's that the water can double as radiation shielding. About 1 meter depth of water surrounding habitats is enough to stop most dangerous space radiation. This is a solution that's being considered for trips to Mars, but would work well for a non-relativistic interstellar trip. By the way, this is an upside of travelling relatively slowly. Relatively minimal shielding is sufficient, and also bumping into a single dust grain isn't going to kill us. The last ingredient to add to our ship's biosphere is breathable air. Just as with water, recycling is critical here. The ISS currently uses a system designed by the European Space Agency called the Advanced Closed Loop System, which recycles carbon dioxide back into breathable oxygen with around 50% efficiency. That's not nearly enough for a generation ship because huge supplies of fresh oxygen would be needed to replenish the losses. Instead, we'd probably need to rely heavily on our natural CO2 recyclers, the plants that we're growing for food. There have been various efforts to build self-contained biospheres capable of sustaining a breathable atmosphere. Maybe the most famous is the Biosphere 2 project, which did okay, all things considered. Yes, they had to install artificial CO2 scrubbers to help the plants, but the project at least demonstrated that a combination of natural and artificial systems could maintain a breathable atmosphere for some time. We have a few decades to perfect this, so there's a good chance that we can come up with an air recycling system that will work over long timescales. So maybe we can keep our crew alive and physically healthy for centuries or even millennia, but will they be happy, and will they stay sane? The sense of isolation on such a long voyage will likely be a major challenge for maintaining the mental health of the crew. We need them to feel connected to Earth, to be part of something grander than their janky little spacecraft on its long journey. The first generation in particular will want to stay connected to their loved ones, but the two-way light travel time between the ship and the Earth will increase over the journey, ultimately reaching a lag of nearly 8.5 years near the end. NASA has done some tests to mitigate the dread that could follow from such separation from our home world. One solution would be the use of virtual reality. Crew members could find solace in digital 3D models of comforting and beautiful Earth environments, and in the case of Generation 1, their homes and loved ones. As the time lag increases, messages from friends and family and well-wishers could be recorded on Earth, beamed to the ship and played back in VR. On our cramped and sterile spaceship, it may be important to grant our travellers certain experiences that we on Earth take for granted. By improving the immersion and interactivity of our VR technology, we may be able to provide convincing visual experiences of mountains and sunsets, the auditory and even tactile experiences of wind and rain, and the olfactory joys of a forest or freshly cut grass. We can't build a Star Trek holodeck, but we can certainly push VR a lot further in the time before launch. Of course, the humans on the ship will still be humans. Arguments will happen, relationships will experience strain, and sensitivity and frustration levels may be heightened due to the isolation and confined spaces. and yet a high level of synergy and teamwork is needed for the mission to succeed. Sometimes a stressed human needs another human, but maybe when tensions rise and trust wanes, it will be helpful to have a trusted third party, one to give advice, to confide in, and to overall receive encouragement from, someone that remembers and learns from the problems of past generations. Maybe we need an AI therapist. NASA has already piloted such a tool named Simon 2.0, the therapy AI robot. Preliminary testing seems promising and is generally agreed that some sort of tool or AI of this form could be very important for the success of a long-term space mission. Our plan so far will hopefully get our crew to Proxima B in good health, genetically, physically, and mentally. But how do we make sure that the mission of the launch crew is still the mission of the landing crew? How do we ensure that the knowledge and skills needed to complete the mission are passed across generations? Or that we preserve the wealth of cultural knowledge and tradition of these once Earthlings? This is where things get more speculative, as there isn't much research to go on. We just know that this stuff is going to be very important and probably very tricky. The shipbound society is going to need a culture and social structure that balances different needs. That structure needs to enable efficient operation of the mission, which may mean clear hierarchies in each operational area, but the culture also needs to promote crew happiness, otherwise we have a revolution in a generation or two. So, an efficient and stable social structure that somehow also promotes mutual respect, individual freedoms, and all the various values that we want this new branch of humanity to carry forward. Overall, it seems at least possible to build a generation ship that can reach Proxima B and to launch in the not too distant future. There are so many things that we know could go wrong, and no doubt many more unknown fail points. And the longer the mission, the more the risk of unexpected disaster. So maybe we really should focus on getting fusion on track. But it's encouraging to think that this sort of sci-fi endeavour is at least within our grasp if existential need or our adventurous spirit compels us. We are the middle children of history, but perhaps we're ready to grow up. Perhaps soon our generation ships will slip the bonds of gravity and distance to explore the new frontier of interstellar space-time.